This is Lab 5, Rotating Reference Frame. I'm John Bratz. The motivation behind this lab is so far we have observed various physical phenomena from a stationary point of view. So we as observers haven't been changing speed or rotating or anything. All of the velocities that we measure are relative to the ground. We don't change speed, we don't rotate. We've been observers in what's called an inertial reference frame. For example, if we are investigating the motion of things riding around a merry-go-round, we look at and measure everything from the point of view of somebody on the ground standing still. So whereas if you yourself were rotating around the merry-go-round, from your point of view, you're not moving at all. Everything else is rotating around you, but from the point of view of someone on the ground, you are rotating around, and it's that difference that I want to investigate. What if we were looking at somebody on the ride, rotating at a constant angular velocity? So imagine you are sitting on the edge of a merry-go-round with a basketball. If you try rolling the ball forward, it wouldn't roll in a straight line relative to you, but from your perspective, it would curve to one side. I think that's easy to imagine. From our point of view, as somebody on the ride, it looks as though there's a force on the ball pushing it out. From the point of view of someone on the ground, there's no force. It's just moving in a straight line, but since it's curving from our point of view, it looks like there's a force. So can we quantify this fictitious force and model in VPython? So the goal is to create a model that simulates motion in a rotating reference frame. And the situation that I'm going to analyze is this video that I found on YouTube of a rotating turntable that somebody places balls onto. The camera's rotating with it, and as you can see, it moves in a straight line. From the point of view of the guy placing the balls on the table, it looks like they're rotating in a straight line because there's no force acting on it. But from our point of view, since we're rotating, it looks like it's curved. So we're going to predict the ball's motion using the model that I'm going to derive and compare the prediction with the data. And I'm going to have to speed through a lot of the technicalities on the math, but I'll just go through the basics. It's a lot to squeeze into 5 minutes. But you can write a position vector in one of two ways. Either you're on the ground, your position vectors aren't changing, there's just xi plus yj. Or from this rotated reference frame, and this point is x prime I prime plus y prime j prime. These primes aren't time derivatives, they're just to symbolize that it's viewed from this other frame. So we can differentiate it to get, on one hand, the velocity measured from the ground. Differentiate this with respect to time. You get velocity as v absolute, measured from the as if you were measuring it from the ground. Differentiate it this way, and you get other terms based on the fact that these unit vectors are changing with time because they're rotating. And you get v absolute, as someone standing on the ground, is v relative, as you, that's what you measure as you're riding around with the carousel looking at stuff, plus this other term, omega times, I'm saying j of r, I'm just saying when you apply j to a vector, it's that vector rotated counterclockwise 90 degrees. And we kind of already know that v equals omega r. J of r just says that it's pointing sideways. Differentiate that a second time, you get absolute acceleration on the one hand, and then on the other hand a bunch of other stuff from the rotated reference frame. From the rotated reference frame, I won't step through it, but this other stuff pops out. So the acceleration that someone on the ground sees is the acceleration that you see as you're rotating, plus these other two terms that arise because the coordinate frame is rotating. You can solve for the relative acceleration that you feel because we want that in our iterative model. And you get this multiplied by mass, you get your forces. So the force that you feel is the absolute force, the real forces that are acting on the object that you're looking at, plus m omega squared r minus 2m omega times this vector that's pointing sideways to v. So you get these other two terms. These other two terms are called fictitious forces. A rotating observer feels two new fictitious forces. One is m omega squared r, called the centrifugal force. It's proportional to distance from center of rotation and points radially outward. So as you're rotating, it feels like something's pushing you out. That's centrifugal force right here. Coriolis force is this other guy. It's dependent on velocity and points in the direction of velocity rotated clockwise 90 degrees. So this is the thing that it causes that spirally action that makes the ball curve. It's perpendicular to velocity. The VPython model that we are going to make that I've made, is the following. Newton's second law still works, so this equation for predicting new positions is still fine. However, the formula for F is now F external or absolute, or whatever you want to call it, plus m omega squared r minus 2m omega jv. Omega is angular velocity. I'm not sure if I mentioned that before. In our case, there is no absolute force being applied on the ball. From an outside viewer's perspective, it's moving in a straight line. So this term is 0, and here is our equation for F. This is what we put in VPython. This is what you get when you rotate V 90 degrees. So you initialize the model, obtain position data using tracker of, again, this video, turntable, and he puts a ball on, and that ball is what I want to analyze and predict. So angular velocity I measure is 2 pi divided by periods, which is 2.19 radians per second. The ball's mass is, I guess it to be the mass of a golf ball, which is about 50 grams. However, the forces, the centrifugal and Coriolis forces are like gravity in that they're proportional to mass. This and this are proportional to mass. So this acceleration that they feel is independent of mass, just like gravity. In the long run, it doesn't actually matter what I put for 50 grams. It's good when analyzing the forces, but all masses accelerate the same. So let's see what we get when we run the model. So this is that world that you see rotating, and that is the ball that you put on the table. Let's see it again. Pretend that this box right here is just stationary on the ground, but since you're rotating on this turntable, it looks like it's rotating. And then, sometime later, someone puts this ball on. This blue is the Coriolis force that's responsible for the curving. This yellow is pointed radially outward, is responsible for that outward pushing feeling you feel when you're rotating like this. And here's the net force. So, results. The graphs of x and y positions for the data and the model correspond well to each other. Here's the x position, here's the y position. They correspond well, however, there are some places where they don't match. If we look at the curve, the actual trace of the path, the yellow looks like it's curves. The yellow, which is the prediction. Yellow is prediction, red is model. Yellow curves too tightly at the beginning, and then it crosses right here and doesn't look like it curves tightly enough. But an error like that could be due to friction from the table or the lens of the camera being off-center. But all in all, our model works, and the centrifugal and Coriolis forces can be used to accurately predict motion in a constantly rotating reference frame.